We left off at filter-based feature selection methods, which are learner independent. So here what I'm going to discuss is two different protocols. The wrong protocol of implementing filter-based feature selection method while combining it with a learner or with a classifier. And then I will introduce the right way or the correct way of doing it. Okay? So first, let's look at this protocol right here. So this is from a very recently published paper by a giant guy in the field, especially on the feature selection research in 2018 in the Journal of Pattern Recognition, an high impacted journal. And in this research paper, I'll put the reference down the video. So in this paper, he discusses the right protocol and the wrong protocol of performing feature selection. So this is what, here I'm going to explain just the incorrect or contaminated protocol for feature selection. So here what do we have? Let me just pick a color, maybe blue. So here we have all the data set. Okay, so this is all samples. We use the whole data, okay, to train or to learn how to select the best set of features. So we input all the data to a feature selection method. So this is a feature selection method, okay? And then after that, the feature selection method, if it's a filter based, it will rank all features, and then maybe we pick the top, okay? Pick top K across all samples, top K features across all samples. Then we're gonna have our subset. This is the subset of selected features, okay? So S is the selected subset of features. Then after that, after selecting the subset, what we do is we perform leave one out on the whole data set. But here, of course, this data set, it's right there. So it's the same data. So I'm taking the whole data, but now it's reduced, right? It's reduced because I selected subset of features. And I perform or apply leave one out, okay, leave one out on to train a classifier C that takes in the whole data that is reduced or the subset of features for all samples. So we're doing leave one out, leaving each sample out, and then training it, then testing it, etc. So this classifier can be an SVM, support vector machines, can be a Bayes, like a Bayesian classifier, etc. And then the output is basically just the accuracy of your classifier, okay? Based on that subset of feature that you selected using your whole data set. Okay, now what is the problem with this protocol? Don't you think this is the right way of doing it? No. What is wrong with this protocol? So, rule number one in machine learning that we saw in the first lecture, the very first rule. We did not, don't what? We have testing and training, don't?
Oh, don't mix training.
Yes, never mix training and testing, okay? So what did we do here? So if you guys notice, we have somehow learned how to select the best set of features using the whole data, which means, just to give you an example, right here. So imagine this is my data, okay? So these are my samples. All feature vectors. So I have N samples, D features, and then I used all of them to find the best features. Okay, then I perform dimensionality reduction, so I can call this X, and then X reduced. And X reduced will be something like this, okay, with less features, but same number of samples, okay? And what I did, I performed, leave one out on this set, which means in the first leave one out, I'm going to leave this subject out, use these guys for training, and test the classifier. But what do you guys notice? That when I learned how to select the D prime or the most effective or the top K, let's call them top K, most discriminative best features, for example, okay? When I learned how to select them, I already looked at this sample. I looked at this sample, right? I was allowed to look at it because I used it. I used all samples to find the best set of features, okay? So this is a very, very problematic, and what we call the peaking phenomenon, okay? So the peaking phenomenon in feature selection, so the data used for testing can be seen previously during the selection process, and you are not allowed to do that, okay? Now that we know what not to do, we should know what we need to do, okay? So how can we define a proper, clean protocol for feature selection combined with a classifier? So I'll give you just a minute to think about it, or 2 minutes, and I'm gonna just write down the variables, but I would like you to think about that. For example, we're using leave one out. So we have something called train learner that takes in some variables, outputs something, okay? And we also have a test learner, like, train SVM, test SVM, for example, okay? Classifier that takes something, also outputs something, okay? And we have somewhere floating around a feature selection method that also takes something and outputs something. So I want you to piece all those ingredients together and create me a clean protocol to train a classifier using leave one out while selecting features. Write it down so you can write down the pseudo algorithm of this, okay? So let's say we're using leave one out and we have n samples. I'm going to give you time, but I'm just saying declaring the variables or defining them. So we have n minus 1 training samples times d. Okay, so Anyone? Guys? So we have our for loop that starts here. And then inside this for loop, for each left out subject, one or more, we're going to do things. Okay, so what is the key idea? What is the clean protocol? Do you have any ideas? Anyone? How should we do this? So here basically we use the whole data set to select the features. Then we perform leave one out on what? On the reduced samples. Okay, so the right protocol is to do what? Any ideas? Guys?
Kind of put together the two circles?
Yes, put together. Good. So we need to combine these two together, which means we're going to use, for example, do leave one out. Or so in this example, I chose leave one out, but you can do, for example, any k-fold cross-validation. So the basic idea is, first, we have an fs method. So the fs method will take what? It will take, if it's, well, we have two options. It depends on what we're using, right? If you are using a feature selection method that is supervised, we're going to write it one way. Or if your fs method is unsupervised, we will write it another way, okay? So here, let's say in the first case where your feature selection method is supervised, for example, using a filter method, it's supervised. So here, what will we give it? The feature selection method. We need to give it the training data. So we're gonna learn how to select the features based on the training. We will never use the testing to learn how to select the best features. So the testing set will be left, outside, okay? And then we're gonna look at what we have. We only have the right to look at the training samples. So fs will take what? xtr, okay, x training. That belongs to the high dimensional space. So since it's supervised, we also need to give it what? The labels or the scores, okay? So ytr, and then the output will be a ranking vector. So r belongs to what? Well, I should write it not this way, but it belongs to what? R? D. Yes, very good. So because it's ranking the D features, okay? Now, if we had unsupervised feature selection, then all we need to give to the feature selection method is what? XTR. That's it. And then we're going to get also a ranking vector, okay? Another ranking vector. But these are two possible options, okay? One of them, we're going to use one of them, okay? Now, the next step, after getting the R, okay, the best, after ranking the features, we need to do what? We need to create the reduced training samples, the matrix X training reduced, which belongs to the new dimension. So to do that, the next step would be to select top D prime features and reduce the dimensionality for training, okay, and testing samples independently, okay? So how does this work? We take our, let's say XTR, and then what we have also, so let me do it step by step, XTR, which belongs to, it's better to write the dimensions. So here we have r n-1 if we're doing leave one out, times d, and then we're going to reduce it to the x reduced training, which belongs to r n-1 samples times d prime. So this means that originally, what did we have? We have all these long feet. Oops, let me just select the same color. So we have all these training samples, okay? And then n minus 1 training samples times d. We reduced it to this new matrix by selecting. So if I select maybe the top D prime features, these are the selected features, okay? So then I'm gonna have reduced the sample 1 to this is the reduced sample 1, then I have another reduced sample 2 by selecting the top D prime features ranked by my feature selection method, and this will be the new matrix, okay? Great. Now, next step, we need to do the same thing for the testing data, because you guys know that we can we train SVM using, for example, training samples of dimensionality D and testing it on samples with dimensionality D prime? No. Why is that? Mathematically. We saw the solution last time. Let me remind you why we cannot train a support vector machine, why this is not feasible mathematically. So if you remember, our optimal solution is a linear combination of Lagrangian multipliers times labels and linear combination of all your training samples. Your training samples belong, if they belong to RD, it means your W star belongs to RD. Now, if you have a new testing subject, okay, this is your new testing subject, it belongs to RD prime. So you want to predict its label. So you're going to take the sign, okay, of X test transpose W star dot product, inner product, okay, plus B. This belongs to RD, and this belongs to a different dimension. You can't do this, right? So it's not possible unless you have the same dimensionality for your training samples and testing samples, okay? Now let's get back to this one. So here, we do the same thing for the testing samples. So we have XTS, the original one. So also XTS belonging to R. I have one sample left out times D. And then I reduce it by selecting the top D prime features. And I will get another X reduced test, okay? Belonging to R1 times D prime. Right. Now we have everything ready almost to train our classifier. So what is the next step? So here we have step 1, step 2, step 3, okay, for these two. Step 4 would be to train our classifier. So we need to train the learner. Train learner. What should we give it? Guys? What do we give? XTR reduced, right? And what else? The YTR. So the number of samples did not change. So we need to give it the label vector, YTR. And then it will return a learned model. Let's just call it M, okay? And then we need to test the learner. So test SVM, for example. So we give it what here? To predict the labels for the left out subject or more subjects. We give it the X, let me just write it that way. So we give it the X reduced testing samples. And also we need to give it the learned model, the hyperplane, for example, the parameters of the hyperplane. And it does the prediction for the testing samples. Okay? And now we have our loop. So you guys can go back to the first example that we saw, whether in Python or in MATLAB. example CV. So you have done classification without any feature selection using just support vector machines. You have many codes available online, like on feature selection, whether in MATLAB and Python. You can try, how to combine those and implement this, code it up. Okay, great. So now you know the right protocol for training a feature selection and combination of a predictive learner. Okay, now let's look at some issues and think about these graphs from the same paper. Now, in the first graph, we will explore together the the influence of the size of the training samples on the performance of a classifier during training, like the fitting error, basically. Okay, and then during testing. So what do we notice here? For example, let's select this first one. So we're training on 50% of the data and also testing on 50% of the data. So we're split the data 50-50. So we have a large number of samples. How many samples we have here? So we have 97 samples belonging to class 1 and 111 samples belonging to class 2. Each sample is represented by 60 features, okay? Now, in the training stage, if we have quite a large data set, not too large, but quite okay, right? So we see that in the training, we have almost 80%, right? We have good performance, and this is while varying the number of selected features. So you can see how the performance changes when we vary the number of selected features. So looking at this curve during training, you can see maybe around 30 features, there was a peak in performance during training, okay? Then you would expect maybe generally during testing you have a similar peak, right? But it's not always the case using the same number of features. Now during testing, this is what we are more interested in learning and boosting. It's the generalization to unseen data. What do you guys notice? There is a big gap, right? So there is a big gap between the training performance and the testing performance. This is the gap. Okay. Now, if we decrease the number of training samples to train on, let's say you select just 10% and test only on 10%. So you can see that training on just 10% of the data, just very small number of samples, you have a very large, I would say, classification performance around 95%, okay, peaking maybe around 20 features or 15 features. But then, interestingly, not surprisingly, interestingly, when you test, your model on the hidden set, there is a big drop in the performance. So you can see that your model cannot generalize. Why? Because first you overfit the data when you trained on very small number of samples, and then when you try to generalize to unseen data, it completely broke down. Okay, so this is one thing we can get from this. Another thing, that just looking at the performance of these models, they largely vary across, when we change the number of features. So for example, training on 50% of the data, or let's look at testing curves. These are the most important curves, okay? Maybe I'll just choose this color. So for the first curve, we get maybe this value as a best feature number to train your model on, so around 38, maybe 35, let's say. The second one peaks around here, and the third one around there. So this is quite problematic. How can you possibly identify the optimal number of features to select to train your model? So these are issues that you can know this or derive by just analyzing these figures. Now let's look at another case. So this nicely compares the wrong protocol, okay, and the right protocol, okay? And here we plot the accuracy. So the pro means it's the right protocol, okay, and the LOO means it's the wrong protocol, just using leave one out after selecting the features, basically, okay? So what do you guys notice? This is using relief F feature selection method, okay? And here what we're plotting just the change in performance for each data set, different examples. What do you guys notice? If we, for example, look at this, so this is using the wrong protocol, and then the real accuracy. So here it's around 90%, here it's not around, I don't know, 72%. So you can see that when you're using the right protocol, there is a big decrease in the data. So sometimes you might get 99%, almost 100%. That's not possible generally. So you might doubt, or revise which protocol you're using to implement your feature selection method. So here you can see for all those cases, if you're using the right protocol, you're gonna always decrease the accuracy, okay? Because it's more challenging. You haven't cheated by picking on, like the testing samples.